Let's do a little nuke. First, stability. I actually have an example of this I didn't do in class. Let me dig that out. I think. Let me find it. Yeah, here it is. Determine if the following are radioactive. Okay. We're going to skip the first one though, so let's do second, the third, the fourth, and the fifth. Yeah, second, third, fourth, and fifth. Okay, so what I would do is find the number of protons and neutrons for each one. So let's do the second one. Protons is 102. How many neutrons? 158? Okay, what can you say about this? They're both even, that's nice. But Z is up over 83, so that's a definite giveaway to radioactive. Okay, Z is greater than 83. Let's try the next one. Protons, I'll do the easy one, is 41. How many neutrons? 50, yeah. 91 minus 41. What can we say about that? Well, protons and neutrons are not equal, but that is not an issue after Z, when Z is above 20. One is even, one is odd, that's uncertainty. What else can you say? Yeah, that's what I was looking for. N is a magic number. So I'd probably guess stable, like that. Okay? Because N is a magic number. Okay, let's try the next one. P is 41. What's N? 51? What do you say about this one? They're both odd. We've also lost our magic number. Let's see. This is, was that niobium? So, it also does not match the periodic table. So, I'd go radioactive. Okay. Next. Protons is 1. Neutrons? 2. What do you want to say about this one? Okay, it does have a magic number. 2 is a magic number. What else do you want to say? However, because Z is small, it's less than 20, protons do not equal neutrons. So I'd probably go radioactive. So if this was a multiple choice and I had to pick the stable one, I'd pick this one, niobium 91. That's the most likely to be stable. Any questions? Yes, in the back.
Why did you say it didn't match the periodic table?
Why did I say that, or what did it mean?
92.
Yeah, 92. That's true for anything. So you can always look, see if it matches the periodic table. If it does, it could be stable. Meaning it matches the numbers you see. So niobium on the periodic table is 93, really. And that's likely happens because it's a weighted average and the most stable nuclei forces that. So, for example, if you saw chromium 52, it's probably stable. Yeah, so stuff like that. So the last one also doesn't match periodic table. So that's another reason to say it's probably radioactive. Is that okay? That's not always going to be true, but something you can look at. Yeah. I'm skipping beryllium. Yeah. Yes, way over there. Magic numbers are given on the exam. On the back. See? Oh, you thought you had to memorize it? No, that's great. That's oppressive. Okay. Can I do one? Should I do one on bonding energy? Okay. And this will be the last thing, then it's getting late. Gotta go home and watch TV. Bonding energy. Oh yeah. Oh yeah, I like this. This is a good one.
If I was there.
Yeesh. Okay, it says, calculate the binding energy of carbon 13. Binding energy. We gave you, on this happens to be on my practice, one of my practice final examples, page 124, number 26. I gave you too much information here, made it too easy. We'll do it the hard way. Okay, so, just so you can see a harder example. Okay, so from the periodic table, he says carbon 6. And then what you do is you say, okay, this is made up of protons and neutrons. How many protons does this have? 6. And how many neutrons? 7. 13 minus 6. Let's see if that works out. 6 times 1 plus 7 times 0 is 6. Yep. 6 times 1 plus 7 times 1 is 13. Yep. So you have to write that by yourself. And then the question will give you this information. The atomic mass of this is 13.00335U. On the back of the exam, you look up the following. Okay, one more time. On the back of the exam, you look up the following. 1.00783U. And this one is 1.00867U. All right. So, what you do first is find the mass defect. That's products minus reactants. That's simple. Products minus reactants. Make sure you multiply 6 times the proton mass. And then 7 times the neutron mass. Because that's what it is for carbon. And make sure you use the distributive property correctly here. That change in mass is a number that I don't know because I just learned about this problem. But it's whatever that calculates out to be. Should it be positive or negative? Negative. We're assuming it'll be negative because there's energy involved in the binding of a nucleus. Okay, and then what you do is you take that change in mass. Okay. All these exceptions. I happened to, I was talking to Chamberlain, and I saw how she solved these problems. They're slightly different than how I solved them. So, FYI. Okay? So if you like my method, you can stick with mine. If hers works fine for you, please use hers. Alright, here's how I do it. You take this, which is in units of U, and then you just convert it to joules. 1.4924 times 10 to the minus 10 joules per U. If you didn't memorize this like me, where would you find this? Back of the exam, of course. Now, this has units of what? Joules per nuclei, but we want the binding energy per nucleon. So what do I do with this monster? I divide by 13 because that's the total number of protons and neutrons, aka nucleons, in the nucleus. And that number is my answer. Done. Any questions? When do I multiply by Avogadro's number if I change to moles? How's this for everybody? Generally good? Okay, awesome. If you have remaining questions, come on down, and I'm happy to answer them.